Okay, so the complex case, the last case, in the homogeneous linear system. So the formula is kind of complex, if you see here. Again, the reason behind it, it's the notion of complex exponentials, but let's not get into that. Let's focus on how we actually apply the formula itself. And as I mentioned before, notice that all you got to do essentially is to plug in 4 quantities, right? The real and imaginary part of the eigenvalue. Alpha comes on the exponential, and beta is basically the frequency, right? I mean, it comes into the coefficient of t in the sine and cosine, and there are some coefficients from the eigenvector. So p bar and q bar will be the real part and imaginary part of the eigenvector. Pay close attention when we find the eigenvector, because you'll have to split it into linear part and imaginary part, because that's how you can extract p bar and q bar. So the main focus will be on the mechanics of how to find these eigenvectors, because once you do that, it's just a matter of plugging in these quantities into the solution. Be aware that if you are in the complex case, you may not be, it's not easy to see the factorization of the quadratic that comes from here. So quadratic formula is the way to go, obviously. So let's set up the characteristic equation. Lambda squared minus the trace. The trace is minus 4, minus 3, minus 1, plus the determinant, which is minus 3, minus 1, minus negative 1 times 2 equals 0. So plus 4 lambda, and this is 5, right? So 3 plus 2. All right, so lambda with the quadratic formula, then it's minus 4 plus minus square root of 16 minus 20 divided by 2. Once you see the negative quantity under the radical, then realize you are in the complex case. So this will be minus 4 plus minus, let's see, root minus 4. If you take out the radical here, that's going to be 2i, right? I mean, remember, imaginary unit, right? Root minus 1. So minus 4 plus minus 2i over 2. You must distribute over 2, because you need to write your lambda in that form into the real plus imaginary part. So that's going to be minus 2 plus minus I. So as I said before, you're going to basically you're going to find the eigenvector corresponding to minus 2 plus y plus I, because you don't have to do it for the other one, they're conjugate. So anyway, alpha is minus 2, save that for later, and beta is equal to 1, the imaginary part. Eigenvector coming conjugate pairs, doesn't matter if you choose the one with plus or minus, just remember your choice. Very important, remember your choice when you split v bar. So again, for consistency, I'm going to choose the one with plus in order to find the eigenvector. And the way to find it is just like before, right? I mean, you're going to pull out the eigenvalue from the main diagonal. You must use parentheses here. Be very careful with the algebra. When I say you subtract minus 2 plus I from the main diagonal, right? You mean you take out minus 2 plus I, the whole quantity, from minus 3. So you have to use parentheses here to avoid algebra mistakes, especially since you're not going to see quickly whether the rows are dependent as they should. Okay, so minus 3 minus negative 2 plus I, then minus 1, and here again subtract from minus 1 minus 2 plus I. And then set up your system to eventually find the eigenvector. So let's continue here. Simplify this. This is minus 3 plus 2. That gives me minus 1 minus I and 2. Minus 1 minus 1 plus 2. That's 1 minus I. All right, so let's pause for a moment, because I want to comment on why actually it's not easy to see that the rows are still dependent. So you better be careful and make sure your computation is correct before you move on. I'm going to make a note here on the top before we continue with this. The rows are still dependent, as they should, but the dependency is via complex coefficients this time. So it is still true that one row is a multiple of the other, but that multiplication factor, it could be a complex number. So you don't have to write this down, by the way, but I want you to be convinced that these two are dependent. It's just not that easy to see. Look what happens if I multiply the second row by the quantity 1 plus I. So if I multiply minus 1 by 1 plus I get the quantity on the top, right? Minus 1, the entry on the top, minus 1 minus I. If I multiply this entry by the same factor 1 plus I get 1 squared minus I squared, but remember I squared stands for minus 1 and basically equals 2. Because of this I squared equals minus 1, it's not at all easy, quickly to see that the rows are dependent via a complex factor. So they're still dependent as they should, it's just that you don't have a visual check as you would have in the real case, when you will see clearly that constant real number multiplied by a row gives you another row. So you have to be extra careful your computation is correct up until this point, because you don't have that visual cue that the computation is correct and the rows are dependent, because the rows should be dependent, right? Just like in the real case. Okay, let's proceed with the eigenvector. Now, which equation you choose? I mean, doesn't really matter as much. Choose the one that feels like it's easier. It's extremely important, though, to avoid fractions when you plug in your choice for V1 and V2. Not because it's a mistake if you have a fraction, but it will make the computation harder when you split it into real and imaginary part if the imaginary unit happens to be at the bottom. Okay, so I want to emphasize that, and if you didn't hear me, let me just state it again. When you write the eigenvector, avoid I at the denominator, at the bottom of the fraction. Avoid that because you will have an extra tedious step to split this into real and imaginary part, because you see eventually I should be on the top, right? I mean, in order to split it into the real and imaginary part. So fractions to be avoided at all costs, essentially. I mean, it's not the end of the world, but again, to make the process smooth, you want to avoid fractions, especially in the complex case. Let me choose the second equation, and this example will be pursued later as well in the following part with the first equation, just to compare the two, because the way you choose the eigenvector may make your answer look quite different, but still correct. So let's choose the second equation. So like I have minus V1 plus 1 minus I V2 equals 0. And how do I avoid fractions? Well, the best way essentially is to plug in 1 for V2. Because if 1 is for V1, when you solve for V2, you gotta divide by 1 minus I. Alright, I don't want that. Okay, so I don't want to divide by 1 minus I to solve for either of these constants. So my best choice will be V2 equals 1. And then V1, of course, if you solve for it, will be 1 minus I. So again, go slow on this part. Therefore, your eigenvector is 1 minus I and 1. Make sure you put the entries in the correct order. V1 is 1 minus I, V2 is equal to 1. Here's another little trick to make things easy and fast at this point. This must be split into a vector plus another vector times I. So you have to basically write eventually this V bar as P plus, not minus, plus I times Q. Why plus? Because I use lambda with plus between alpha and beta. The easiest way to make this split is to write both entries in the form alpha plus minus I beta. So if, for example, one entry doesn't contain I, like the second entry in my case, make it to contain I by legal means. So that means, just write 0 times I. So arrange it like that, I mean, each of the entry has a standard complex number. Real part plus minus imaginary part, real part plus minus imaginary part. Because with this arrangement, I hope it's pretty obvious how this splits into the real part and imaginary part. You split the matrix as a summation of, in this, between the two. 1, 1 will be your P bar. and then plus between them, and what's left times I will be your q bar. That's the hard part essentially, or the tedious part. Gotta be very careful on this, right? So extract the eigenvector, the easiest one you can find, split it into real part, imaginary part, and that's your P and Q. And we're gonna do, probably we're gonna have room here. I'm gonna do the other equation to see the other version of it. But let's actually save this here. So for once, what do I have? I have alpha minus 2, I have beta equals 1, and one version of P is 1, 1, one version of Q bar is minus 1, 0. I'm saying one version because if you choose the other equation, when you solve for the eigenvector, you're going to have a different P and Q. So we're going to write a solution using both versions, solution given here, but I want to basically, and that's optional by the way, I mean you don't have to do it, you do it only once, right? I mean you don't have to put two versions, but I want to use the first equation just to emphasize that your choice of the equation may make the solution look quite different, because P and Q will be different if you choose the first equation, although the solution will still be correct. So what if at this stage here I'm going to choose the first equation? So the first equation will be minus quantity 1 plus I V1 plus 2V2 equals 0. How would I extract the eigenvector? Well, here I have to be very careful. Remember, I want to avoid fractions. You definitely don't want to give, what do you want? You don't want to give V2 equals 1. Because again, if you solve for V1, that forces you to divide by 1 plus I. You don't want that, right? You don't want I at the bottom of the fraction. On the other hand, let's see, you can plug in 1 for V1, but that means you have to divide by 2. That's still fine. You may have 1 over 2 as a fraction, but the best choice that avoids all fractions altogether, if you look carefully, is V1 equals 2. Because that allows you to simplify it with this one here. So if I let V1 to be 2, then I can divide by 2 both sides, and then V2, the second entry, move that over. That's going to be 1 plus I. That's the nicest combination. So therefore, your eigenvector in this case will be 2, the first entry, and 1 plus I, the second entry. So that's why the solution looks quite different, because you see this I can happen at the first or the second component. You know, when you do the split into P and Q, the P and Q could look quite different, and you may wonder, am I wrong or not, especially if you compare it with the back of the book, right, with the formula sheet. Excuse me, with the back of the book answer in the textbook. But you know your answer is still correct, and I'll prove it to you on the next part, that if you impose an initial condition, you're going to get the same solution. Doesn't matter which format of the general solution you pick. So let's do the trick like before. Split this into linear and real and imaginary part. 2 plus 0i, 1 plus I. Clearly, you get 2, 1, and then 0, 1, I. And obviously, this will be P, and this will be Q bar. So another version, keep that in mind, write it in your notes, because I'm going to use it next time. Another version for the problem is alpha minus 2, beta 1, P bar equals 2, 1, and then Q bar equals 0, 1. So you can write a solution with either of these. Let me see if I have some room here. Maybe we have room to write solutions in both. So I have it in the same screen. But I'm going to write it on the next part as well for the same example. So let's see you use this version, right? That means your solution is C1 e to the alpha t, which is e to the minus 2t. So it's challenging here in the complex case. Let's see, so you have P 1, 1 cosine of beta t, that's cosine of t, and plus or minus Q bar, which is minus 1, 0 sine of t. We're going to write it in nicely on the second part of the lecture. And then of course the second combination, which is plus C2 e to the minus 2t 1, 1 sine of t plus minus 1, 0 cosine of t. Okay, so that's one way. And if you use the other eigenvector here, then you have the same combination but with different p bars and q bars. So here p bar is 2, 1 cosine of t minus what was q bar 0, 1 sine of t, and then plus c2 e to the minus 2t 2, 1 sine of t plus 0, 1 cosine of t. Both are correct. Let me say again, both are correct. You obviously don't do both of them, right? You just choose one and be done with it. And I'm going to show you that they are correct because they will give you the same solution once you impose the initial condition. So we're going to have a final part shortly, continuing with this example, but putting now an initial condition into the problem. Stay tuned.